Okay, good morning everyone. This is our last formal lecture. I imagine you are very happy. See a lot of happy faces. but so today we are going to talk about input parameters, right? And maybe why do we care about input parameters? We have been working on developing models to get some output of interest, which can be cost, thank you, health, utility, or other outputs that we are interested, like the number of strokes or time to X, for example. So these are the outputs that we are interested in, and we need these to make decisions, to make resource allocation decisions. So our model also had some inputs. So these are our parameters, such as the cost of some interventions, the utility rates for treatment effectiveness. So these are our input parameters. So our model essentially transforms our input into output. Okay. So clearly, what we will get out of the model will be a function, or will depend on what we are feeding the model. Okay. So the reliability of our estimate for cost, or our, when we are doing cost effectiveness analysis, or any recommendation we make using our model, depends on what we are feeding the model. Okay. There are several important reasons why we need to spend some time on inputs. The first one is we often have some intuition or evidence about the behavior of our model if we change some of these parameters. So for example, we know that if we increase the cost of a treatment, then we expect that the cost of the treatment for a patient that we calculate as an output also increases. Right? Does it make sense? Or if we increase the effectiveness of a treatment, then we expect, for example, the number of lives that we save by using the treatment goes up. Okay, so we often have some intuition about the behavior of the output if we change some of the input parameters. So, and that is one of the important ways to validate your model. Okay, so this is one of the standard ways that you can change one by one the value of each parameters and see if the impact or if the behavior that you see in your model output matches your expectation. If it doesn't, might be something wrong with the model, there might be a bug, or it might be a new insight that your model is generating. It would be a new evidence. But again, it's something that we need to make sure it's not a bug or it's not a mistake. It is actually some evidence that the model is generating. But often we have some good intuition about the behavior of the output in terms of our input. So that's reason number one. The other important reason that we investigate the inputs is that what we are trying to capture is the expected value of these outcomes. So that's what we are interested in. That's what we have been trying to do, to find the expected cost, the expected health utility, or the expected number of strokes. All right. So if we assume, if we use G to represent our model, and if X is our input variable, what we want to get is the expected value of outputs that are a function of X. Right? So X is our input variable. Imagine it's cost, utility, treatment, effectiveness. Choose a value for X. If you run your model, that's our G, then we get a sample for output. When we run it multiple times, we get many samples, then we can estimate the expected value of the output, right? Now, if we use only the expected or the mean of each parameter, then what we get is G so let's put it this way. We have this, we are using this value for our input value. So for example, treatment effectiveness of 90%, right? But where did we get it from? So usually we refer to scientific literature, for example, all right? And if you pay attention, you see that it always comes with some confidence. So for example, let's say that the expected treatment effectiveness is 90%, but it might vary between 75% to 95%. So there is usually uncertainty around the parameters that we use in the model. Okay? So we need to be able to capture this uncertainty because the true value of treatment outcomes may be anywhere on this range. If we use 90%, then we are using the mean of this variable. This is what we get. So if you, in your model, we only use the expected value of the input parameters, this is what we get. But what we are interested is this one. And these two are not necessarily equal. All right? Do you know the condition where these two expressions are equal? So G is our model, X is our input parameters, all right? This is what we want to get, the expected value of cost, health utility, number of strokes. This is when we use the mean of each output, the mean of each input. So instead of, I go with, instead of capturing the uncertainty around cost, I just go with, $50, for example, the utility 0.1, although they are varying over a range. So if I just go with the mean, this is what I get, right? So these two are equal only when our model is linear. Okay, but as we saw, I mean, in many of healthcare problems that we have been working on and the models that we've developed, our models are not linear in terms of the input parameters. Okay. So two main reasons to investigate the impact of inputs. One is we can use it as a way to validate our model. We can set the cost to a lower number than the expected value and the upper number. For example, if our cost is $50, if that's the estimate we have, let's run the model once with $40 and once with $60. Okay? We expect that when we increase the cost, we also see the average cost of each individual. If that's the behavior we see, we feel good about this parameter, and we feel good about the behavior of the model. If, for example, we increase the cost, and then it ends up that the total cost goes down, there might be something wrong with the model, right? Similarly, if the treatment effectiveness, we improve it, we expect to save more lives, we expect to gain more quality of adjusted life, for example. So that's reason number one. Reason number two is that we have uncertainty around the estimates that we are using in the model. Okay? If I use 90%, the 90% comes from some, for example, clinical trials that use a limited number of patients. So I know the treatment effective is 90%, but it might vary between 75% to 95%. Now, if I increase the number of patients in that clinical trial, this range might be shortened. Okay, so we need to be able to reflect that into our decisions. So that's reason number two, that we do. We need to capture and describe the uncertainty around these parameters. parameters. So let's, you don't need to open this file. Let's just have a look at what we had developed before using our continuous time Markov model with for the HIV example. So this is essentially the list of the inputs of this model. Okay. Now what? For some of these inputs, we have some rules to inform the value. For example, the number of replications. How do we decide about the number of replications? Why did we go with 250? Why not 50? So what impact I would expect to see if I increase the number of replication to 1,000? Say it again? Yes. So if I increase the number of replication, then if you look at, for example, the time to AIDS. If I'm interested in estimating time to AIDS, so my sample mean is, for example, here 15 years, and here is my confidence interval. If I'm not happy with the length of the confidence interval, I can increase the number of replications. So if so let's remember, this is now between 40 to 16 and a half. Now, if I increase it to 500, it takes a while. Yeah. Anyway, you see that now the confidence interval is much smaller. Okay, so now if I want to know in terms of time to AIDS which alternative is doing a better job, I need to make sure that this confidence interval do not overlap. Okay, so we need to increase the number of replication as much as possible so that these confidence interval do not overlap, so that I can make some claim or make some conclusion about the performance of combination therapy in terms of time to AIDS. Okay, so there's some rule to decide about the number of replications. Right, so increase it. If you are comparing two alternatives, increase it so that the confidence interval do not overlap. Right. What do we have next? So we have cycle length. We discussed about how to decide about cycle length. Remember, we did some calculation on this sheet to make sure that the number of the probability that two or more events occur during the cycle length is relatively negligible. So that's how we decided about the cycle. Okay. Initial patient age. So this is, it can be specified by the user of this model or the decision maker. So this is my cohort. I like to run it from age 40. Now, if I change it to age 10, that means that I need to probably change some of the other parameters because the mortality rate is different for, people of age 10. Or if I change it to 60, I probably need to change some of the parameters. But this is essentially specified by the user. Okay. The discount rate, we use 3%. This is the common value that you see in the literature. You can also decrease it to 1% or 5% and see if your recommendation would change. Right? So that's essentially one-way sensitivity analysis. Okay? We change the value of one parameter, we put it to a lower bound and an upper bound, see what impact it has. Usually, we don't see much impact on the recommendation, so you can just report that we did sensitivity analysis on the discount rate and our recommendation didn't change, right? If it turns out that you, for example, increase the discount rate to 5% and then suddenly you are now making a different recommendation, that means that the model and your recommendation is sensitive to this parameter, so we need to go and find a more accurate estimate for discount rate. But again, this is what you see in many papers at 1%, 3%, 5%. Okay? And usually it doesn't have much impact on the recommendation. Now let's have a look at the other parameters. So these are the parameters that to inform we use data. Okay? The first one is the annual background mortality rate. If you remember, we use some census data or CDC data. So the report was that in year 2015, the mortality rate in the US is 8.15 per 1,000 individuals. Okay? Now, do we have any uncertainty around this estimate? Is that the true mortality rate for the US in 2015? What would make it a true estimate for the true value of mortality in the US?
If you had like a census and you like surveyed every single person.
So exactly. So if this is our entire population and has, for example, n member, if we follow all of them, you know, in a year, and at the end of the year we see that okay, n, for example, I don't know, m individual die, then m divided by n is the true mortality or the probability of mortality for my population, because I'm looking at the entire population, every individual, okay? But if I'm gathering samples from a subset of these populations, such as for example N1, then and among these individuals, M1 died, then M1 over N1 is just an estimate for the true mortality rate. Okay, so there is uncertainty around it because I'm not looking at the entire population. What we want to do is to capture the uncertainty around this estimate in our model. Okay, and see if that changes anything. Right? Another example is so imagine that we have 20 patients with stage 4 cancer. We followed them for a year, and 5 of them died. All right. So what is mortality here? Mortality, the probability of mortality is how much? 25%. Yeah. Okay. Now, if I have 250 die, same story. So both of them gives me the same estimate for the mortality rate, but I have more confidence in this estimate because I have a larger data set. Okay, does it make sense? Yeah. All right. So this is what we want to do today. And treatment relative risk. This is what we extracted from the literature. We will look at it. We see that there is a confidence interval associated to this. Okay, so we need to capture it. The annual cost. This is what we use, but again, we can't say with 100% certainty that this is the annual cost of every single individual in our model. There's usually variation in the cost, so we are going to include that in the model as well, and also the utility, right? So let's open the first part of the lab. the parameter uncertainty part 1 is the setup. Do you all have it? Right. So on top, we have some inputs that, again, we didn't use data to inform them, so we leave them alone. Number of replication, we have some rules to decide about number of replication, cycle length as well. This is our core, and the discount rate. If you want to see the impact, put it 3%, 5%, see if anything changes. So these are not informed by data, so I separated the other parameters. These are the parameters that I have uncertainty around because I use data to inform them. Now here on this table, this is what I know about this parameter. So I know that the annual background mortality is coming from, for example, census data or CDC. So this is a pretty accurate estimate. So I don't have any uncertainty around the mortality, again, because we are looking at the entire US population, not just a subset of the population. The treatment relative risk, this is the number that we used before, but if you look at the initial report, we see that there is a confidence interval around it between 0.365 to 0.71. Okay, we use this estimate for the cost of being in the first state. Now, again, as I mentioned, there is no way to ensure that every patient costs this much. So I'm going here to assume, since I don't have access to the cost data, I'm going to assume that the standard deviation is 1/4 of the mean. Okay, this is my assumption. It's okay to make assumptions, okay, as long as they make sense. So this is my assumption here. This is the expected cost of each individual in this state, but the cost varies, right? And this is the standard deviation. In an ideal world, we have the cost data, and we can calculate the expected value of the average, the sample mean, and also the sample standard deviation if you have the cost data. But I didn't have it, so I just assumed that the standard deviation of cost is just 1/4 of the mean. Okay. Similar for the annual cost of the two drugs that I'm considering. The annual cost of monotherapy is just equal to the annual cost of the zidovudine, and the annual cost of combination therapy is the sum of these two costs. All right. So I don't have any uncertainty particularly around those because those are determined by the cost of the drugs. All right. So it's determined. So the uncertainty around them depends on the uncertainty around the cost of the drug. So I leave them alone. Then I have the utilities. I didn't use any published study. I assume that this is what we have. Again, ideally we should be able to extract these utility rates from published studies. And again, if you look at them, when they report, there is usually some uncertainty around them to capture the differences between patients. So this is the standard deviation that I'm assuming for the utility rate in the first state. I'm assuming that it's 1/5 of the rate, the standard deviation. So there is a variation in my patients. Yes.
I'm sorry, can you just explain again why we're not putting the cost of the monotherapy and combination therapy in?
So we will do it because we assume that the cost of monotherapy is equal to the cost of this drug, and the cost of combination therapy is the sum of these two drugs.
So since those two are already accounted for, we don't need to put them in?
Yeah, we will do it later, so I will explain. So this part is just what we know from the literature, for example, or from our data. This is what our data is telling us. and then based on this we calculate the cost of monotherapy. Because the cost of monotherapy depends on the cost of first drug, and the combination is the sum of these two drugs. So we'll see in a minute.
Oh.
Okay. So this is what I know from the literature. This column is the value that I'm going to use in the model. This is what we had before. So if you look at the names, you see that this is the annual background rate. This is the treatment relative rate. So this is where the model reads the value of input parameters. Okay? Now, if I want to continue the way that I did it before, use the mean of parameters, then the value here is equal to this. The value here is equal to this. Okay, this is what we did before. All right. But what I want to do now is to be also able to use samples of from the distribution that I'm going to use to describe the uncertainty around this parameter. So we will see again in a minute what's happening, but maybe so let's okay, first step, I want to be able to turn on and off the uncertainty analysis. So I want the user to be able to run the analysis using the mean estimates, and once using the samples that I'm going to generate from the probability distributions. So let's put maybe on and off here, and I want to generate a list from which the user can specify whether the uncertainty analysis is on or off. So you can click on the cell C7. We go under data. Oh, if I remember, no. I think it was a little bit different. So it is under data and then data validation. So here, change the criteria to list, and the source of this list is here. Okay. I can do it again if you think that's useful. So if you do it, then you can pick from on and off for this cell. Okay. Should I do it again? Yeah, okay. So put on and off here on anywhere you like, and click on the cell C7, go under data and data validation. You can click on data validation, right? Then under criteria, select list, and the source is here. Right? Then click OK. All right. So now I can turn on and off the parameter uncertainty analysis. Now I need to decide what value to use in the model. For the annual background mortality rate, I mentioned that there is no uncertainty around this estimate because I look at the entire US population, so I can just set it equal to the mean from the reported data. Okay. Now for the treatment relative risk, if the parameter uncertainty is on, I want to use the sampled value that I will generate in this column. And if it is off, I will go with the estimated mean reported in the data. Okay, does it make sense? So this is the estimated mean reported in the data. This is what we have been using so far, right? Now I'm going to use different probability distribution functions to capture the uncertainty around this parameter. When I'm doing parameter uncertainty analysis, I'm going to generate samples from those distributions and put them here. Okay? So if the parameter uncertainty is on, I want to use these samples in the model. If the parameter uncertainty analysis is off, I will use the mean, similar to what we did before. Okay? So let's we can copy and paste it down to here, because for all of them we have a significant uncertainty around the estimates. So I want to be able to use the sampled value. So if I turn it off, then I'm going to use the mean reported in the data in the model. And if I turn it on, then I will use the samples that will be generated on these columns. Okay. So remember, the cost of monotherapy is just equal to the cost of first drug. The cost of combination therapy is the sum of two drugs. So turn it off. This is what we get. Okay. So these are the numbers that the model is reading. Okay. This is what is reported in the literature. And this part, I'm going to use different distribution to describe the uncertainty. I will use this distribution to generate samples. And if the parameter uncertainty analysis is on, I want to use these samples in my model. And if it is off, I want to use the mean estimates that we had before. All right? For the last three parameters, also we want to be able to do uncertainty analysis. So again, we can use the same formula. If the parameter uncertainty is off, use the reported means. If it is on, then we want to use the sampled value on this column. So if you have fallen behind, that's okay. We can, if you open the next file, this is already set up, so we can continue working on that. Okay, so let's now open the part 2. Okay, so let's just start with the cost. That's the easiest. Those are the easiest parameters to describe the uncertainty. So let's look at okay, for cost parameters, we have one requirement that every sample we generate for cost should be greater than 0. Okay, cost cannot be negative. That's our assumption. And one of the popular distribution to capture the uncertainty around cost is gamma distribution. That has some as a PDF that is something like this. So it starts from 0 and it goes to infinite. Okay. So what I want to do is to fit a gamma distribution to my data, right? So this is if X follows a gamma distribution, and gamma distribution has two parameters, alpha and beta. So if this is the expected value of a gamma distribution is equal to alpha times beta, and the variance is alpha times beta to 2. Okay? Now, if you look at your data, your cost data, it is easy to calculate the average of cost, and also it's easy to calculate the variance. Now, if you have the cost and variance from your data, then you can solve these two equations for alpha and beta. Okay, that's how we fit a beta distribution to our cost data. So in my model, I assume that I have this data set that I was able to calculate the mean of the cost and also the standard deviation. So I have the mean of cost and a standard deviation. Now I can fit a gamma distribution to this data. All right. So we can just use these two formulas. So if mu bar is our sample mean and S2 is our sample variance from our cost data, we can just use these two equations to get alpha and beta, two parameters of a gamma distribution. So let's do that here. So we mentioned that alpha is mean 2 divided by the variance, which is the standard deviation, right? So that gives me the alpha. This is one of the parameters of gamma distribution. So all the cost parameters follow. I'm going to assume that all the cost parameters in my model follows a gamma distribution. So you can easily calculate the alpha parameters for all these cost variables. Now, beta is the variance divided by mean. So variance is the standard deviation to 2 divided by mean. Okay. So again, imagine that you have this data set of all these patients. You can extract the cost of, for example, being in a state CD4 between 200 and 500. You have the data to estimate the sample mean of the cost, and you can also calculate the standard deviation using your data set. Now, recognizing that patients have different costs while they're in this state, we want to randomize the cost that we use in our model. Okay, we mentioned that one of the popular distribution to capture cost is gamma distribution, and the way that we can one way to fit a gamma distribution to our data is to match the expected value and the variance. And that's what we did here. We are finding the alpha and beta parameters of gamma distribution. Okay. So now if I want to generate realization from this distribution, what was the approaches that we discussed before? If I have a probability distribution function, I can sample from the random variable. How did we sample from the exponential distribution? You remember? If x follows an exponential distribution with some rate, remember we discussed about how to generate realization of x or sample from x. which was the inverse transform. Remember, we used it in our discrete event simulation. So the inverse transform is that we need to find if we have the cumulative distribution of a random variable, then we can generate a random number between 0 and 1, and then find the inverse of the cumulative distribution, and that gives us one realization of our random variable. So for gamma, fortunately, Excel has a function that returns the inverse of gamma distribution. So we can use it here. So we have gamma inverse, right? So we need to pass a random number between 0 and 1. And gamma distribution has two parameters, alpha and beta. Alpha is here, and the beta is here. Okay? Does it make sense? So I fit gamma distribution to my cos theta. These are the two parameters of the gamma distribution. Now I want to sample from this distribution. Okay, and Excel has gamma inverse. So I need to pass a random number between 0 and 1, and also the two parameters of the gamma distribution. Now, every time I hit again F9 or refresh, I get a new sample from the gamma distribution that I fit to the cos theta. Okay? Now, if the input uncertainty analysis is on, then I'm going to use these samples in the model. Right? So we can copy and paste it down. So again, if you refresh, every time I get a new sample for cos. Are you with me? Is there any questions? Okay. So that is, cost. So this is how we capture the uncertainty in our estimates, in our parameter estimate. So if I'm 100% sure that every patient will have the annual cost of, for example, 3,000 while in this state, then I don't need to do this. Okay, so if you're sure about the cost and these variables, then we don't need to do uncertainty analysis. In reality, however, these costs may vary. The cost of being in a state might vary among patients. And that's why we generate these samples so that every time we run the model uses a new sample, a different estimate for the cost. Okay? Right? Question? Yes.
Yeah, I was just wondering, so in another class, we use something called the tornado chart that shows like how much the results vary based on the parameters. So this doesn't do that, but is there a way to do that?
So that is I know many people use that approach, but that doesn't capture the uncertainty. What they does is that each of them, you vary this parameter once lower and once up. It is not bad. It is
fixed, right?
Assuming that the rest of the parameters are fixed. So that gives you some insight about the behavior of your model. So you see that, okay, I increase the cost. I expect to have that makes sense. But it doesn't solve this problem that we talk about it, that you have the model, this is your input variable, this is what your model generates, this is what we want to get. But if we use the mean, if we don't capture the estimate, then we get a biased estimate for this, because there's uncertainty around this. If we ignore this, this is not going to be an unbiased estimate. So it doesn't solve that problem. The other thing is that when some of these parameters are informed by data, the quality of data is different here. So we need to be able to capture it. If I'm using thousands of patients to estimate this one, is very different from just 10 patients. So that's, again, the one reason that the tornado chart doesn't capture that. So that's it, what we are trying to do. Yeah. So this is cost. And of course, if you think that your standard deviation is much lower, you can reduce it, and you see that the variation in estimates goes down. Okay, so that's how it works. All right, now let's talk about the utility weights. There are for utility weights, the choice of which distribution to use depends on how we calculate the utility weights. So in many instruments, if you remember, we had these instruments that ask patients to rank their, I don't know, maybe I have it somewhere here, but let's see. So in the value of life, we talk about it, if you remember. So yeah, on the first class, so we have this instrument to estimate the utility. So it asks some questions, does some calculation, gives you a weight. So if the estimates that they provide is always between 0 and 1, 0 means death, 1 means perfect health. All right, so if the estimate for utility that you get is always varies between 0 and 1, then a common distribution to use is a beta distribution. That again have something like this, you can get something like this. So it is a very flexible distribution. So if it varies between 0 and 1, we get beta. Some instruments might return also negative weight for utility, which represent the states worse than death. We saw a couple of examples before. So then 1 represents perfect health, 0 is death, and the weight below 0 is states that are worse than death. So if this is the utility weights that you use, then they use gamma. We can talk about it later, but it's a little bit complicated, so we'll forget about this. So assume that our utility weights are always between 0 and 1. Okay. Now, in our example here, this is the mean that I had. Imagine that I extracted it from some studies, and this is the standard deviation of this. So again, I want to use the same method, the method of moments, to fit a beta distribution to this data. So if you want to fit if I have a beta distribution also have two parameters, alpha and beta. The expected value of a random variable distributed according to beta is alpha over alpha plus beta, and this is the variance. So if you look at your data, and if you have an estimate for the mean and an estimate for the variance, you can solve this equation here and get find alpha and beta for your distribution that fit your data. So this is the two formula that we are going to use here. All right, so I want to fit a beta distribution to the utility in this state, which has the means 0.75 and the standard deviation 0.15. So we do the calculation here. All right. So we need to first calculate alpha plus beta. So according to this equation, the alpha plus beta is, let's follow this one. So the sample mean times 1 minus the sample mean. Divided by the variance, which is here, and minus 1. Okay, so if you have some data, calculate the sample mean, sample standard deviation. If you want to fit a data distribution, beta distribution to your data, this is how we do it. Okay, we first calculate the alpha plus beta. This is the formula. And again, according to this formula, alpha is sample mean times alpha plus beta. So alpha is, this is the sample mean times alpha plus beta. They make me say?
That's in alpha, right? Not beta.
Oh, thank you, yes. All right. So I have alpha, alpha plus beta. So then beta is just alpha plus beta minus alpha. Right? This is how I fit a beta distribution to the utility weights that has this sample mean and standard deviation. Okay. Now I'm going to use the same method, the inverse transform, to sample from this distribution. So the sample value is located here, so I'm going to use beta inverse. I need to pass a random number between 0 and 1. The alpha is located here, and the beta is located here. Okay. Again, whenever I refresh, I get a new sample for the utility weight in this state. Right? Let's copy and paste everything down. Is there any question?
Can you go back to calculating the alpha plus beta?
Yes.
Are those the two main distributions we use?
So we are going for each parameter, we need to use a distribution that's suitable for the parameter. Yeah. So if we, again, a step back. So this is, if I have 20 patients, 5 dead, I estimated mortality rate to be 25% here, right? Again, 200 patients, 50 days, 50 dead, same mortality rate. But here you see that I'm fitting a beta distribution to this data. You see that this is tighter compared to this. So that means I have more uncertainty around my estimate here compared to here, right? So if I use the 25%, I'm treating these two data sets equal. If I run my model with 25% mortality, I'm ignoring the fact that these two data sets have different number of patients. That's what I'm trying to do. If I have more patients, I want to sample the mortality from this distribution to capture the uncertainty. And if I have less data from this distribution, I'm less certain about my estimate in this scenario. Right? Does it make sense? All right, so we are good with the utility weights and the cost. And now let's go with the treatment relative risk. So this one is a little bit complicated, but not as complicated. So how do we estimate the relative risk of a treatment? I think many of you have seen this table. So we have treatment group, control group. Event present here and event absent. So among treatment group, for example, if you're talking about mortality, A, experienced mortality, C, event. So we have ED here. So the relative risk is defined at this equation. So A divided by A plus B, and then divided by B plus B plus C. Yeah? So this is the denominator is the risk of having the event under treatment group, and this part is the risk of having the event, experiencing the event under control. So when we calculate that, this is an estimate for the relative risk. Okay. Now you, if this is what we have, if you calculate this, that will be an estimate for the relative error. Now we want to calculate a confidence interval around this estimate. The way that we do it is take the ln of this expression, then the confidence interval, the 95% confidence interval, is calculated like this. So this is our estimate. We take the ln. This is the 1 minus alpha, half alpha percentile of the standard normal distribution. And this is the variance, this is the sample variance of this expression. And we take the square, so this is the confidence interval that they report. So the confidence interval that you see is coming from this calculation. So now, this is what is reported in the literature. Now I want to be able to sample from the distribution that can fit to this measure. So if you have L, lower band of this confidence interval, and you have U, the upper band of this confidence interval, then we can, the confidence interval of the estimated relative risk, we need to raise it to the, we need to calculate the exponential value of these two. This is a standard approach to find the lower bound and upper bound for the relative risk. So if you want to take a let's see. It's also confusing for me. So this is let's review it. So we have so this is a calculate the point estimate for the relative risk. That part is easy. When we want to form a confidence interval around relative risk, then they assume that relative risk follows a log normal distribution, and then they calculate the upper bound and the lower bound of the log of the ln of the relative risk, and they report this one. All right. Now, what I want to do is use this confidence interval to go back and be able to sample from the relative risk. So this is what is reported, not this, but this is anyway, let's do it and you see. So there's a back and forth between. So they calculate the relative risk. They assume that the relative risk is distributed according to log normal distribution. They use this assumption to report the lower bound or the 95% confidence interval. Now we want to move back from what is reported in the literature to be able to sample from the relative risk. Stay with me, all right? So if U is the upper bound that they reported, and L is the lower bound, then the sample standard deviation is calculated according to this. So let's do this here. So we are working on the treatment relative risk. So the standard deviation is the upper bound I'm worried that I'm making a mistake. Check something. Right. So the standard deviation, we need to we take the ln of the upper bound minus the ln of the lower bound. We divide it by 2. And normal distribution. Okay. Let's see if it's working first. Yeah, let me just copy and paste this. Yeah. All right. So what we are doing here is that in the literature, what you see is they say, okay, the treatment relative risk has this mean, and they report the upper bound, lower bound for the relative risk. Okay. Now, what I want to do is to generate samples of this relative risk. Okay. In order to do that, I need to characterize the distribution, the probability that distribution that fit this relative risk. Okay, and that's why we should look at how they calculate the relative risk and the confidence interval. So they assume that the relative risk follows a log normal distribution, and that's how they calculate this confidence interval. Now we need to transform everything back into log normal so that I can take samples from log normal. So that gives me the standard deviation, and the mean is simply the ln of the mean. Yeah. And this one? Okay. All right. So if you look at the literature and you see that the treatment relative risk is reported, okay, the first thing to check how they calculate it. Most of the time they use they use this approach. They essentially assume that the relative risk follows a log normal distribution and how they calculate the lower band and the upper band. Okay? Now, if you want to take a sample, we need to go back and find that log normal distribution. And the way to do it is here. There's just some steps that you need to follow. If you have the upper bound, lower bound, we can find essentially this part is the half length. So upper bound minus lower bound divided by 2 is the half length. When you divide it by the normal inverse, that gives you an estimate for the standard deviation. So remember in our, if you have x plus minus, you have z alpha, and some estimate. So this is the general formula. So you have some, this is the upper bound for upper critical level normal distribution. This is some estimate that you have for the variance and x. So what we have, if we have the upper bound, lower bound minus lower bound divided by 2 gives you this. Okay? Right. So this is the log normal. Now taking so if you want to take a sample from log normal, this is the approach that we use. So we have normal distribution. So to sample from a log normal distribution, we first generate a sample from a normal distribution and then calculate the exponential. So again, if you refresh your sheet, you see that now we get samples are around the value that they have provided in the decision. Okay? All right, so that's all for this side. Is there any question? Would you like to spend more time on this?
So it's not fair, but say you didn't have the treatment relative risk and you just had transition probabilities like within a matrix. Is there a way to do that?
So we will do it next. Yeah. Okay, so I hope you are getting the big picture. The big picture here is that you might have some data set to estimate some cost or the sample of the sample mean of cost, and you might estimate some other measure like the utility, and you might use the literature to get an estimate for the treatment relative risk. The idea is that there is always uncertainty around these estimates. So now what we are doing is to find a proper distribution function to capture this uncertainty. Okay? If you have, for example, the case of utility weights, we know that they vary between 0 and 1, so that's why the beta distribution is ideal. And if you have the mean and the standard deviation of your utility weight, you can fit a beta distribution to the data. And then you use samples from your beta distribution in your model. If you have cost, gamma distribution is usually a good choice because it is bounded from below, so it goes from 0 to infinity. And cost also can go from 0 to infinity, so that's why people use it. So if you have the mean and standard deviation, we know how to fit a gamma distribution to the cost data. So that's what we do. Now the final step is these, capturing the uncertainty around these probability transitions. So we had this data set from UK. They followed a group of patients. They checked their CD4 count at the beginning of the year and the end of the year, and they report these counts. Okay. Now again, if I have instead of 1,700, if I have 17,000 patients, I would be more confident about the probability transitions that I estimate from this data. Now, what I want to do is to again capture that uncertainty in the model. Okay. So. If I have, imagine I have 10 patients, and at the end of the year, with probability P, I have death and survive, and 1 minus P. Now, if death is my random variable, what is the distribution of this random variable? Remember from the probability class? So there is I have a group of patients. There is a probability of success or failure. Now, X is the number of deaths. What distribution does X have? Binomial. Yeah, so it has a binomial distribution. The parameters is N and P. Is that right? So P is the probability of success, or whatever we call success here, death, we assume is success, and N is the number of the samples, right? Now, if I have again N10, but I have P1, P2, and 1 minus P1 plus minus P2 to, for example, I don't know, maybe natural death, disease death, and survival. So now I have 3 outcomes. Now x1, x2, x3. What distribution I can use to describe x1, x2, x3? I have 3 outcomes, and it's the same. Multinomial. So it has So it has a multinomial distribution, and is the size P1, P2, and essentially P3 are the parameters. Okay? So you have a group of patients with some probability they may end up in different groups. All right? So it has a multinomial distribution, it's binarized. Now, what we are doing in this lecture is to capture the uncertainty around P. We don't know P, okay? If you have this experiment, it turns out that among N patients, M is dead, then P, the point estimate for the probability is M over N. Is that right? Okay? Now, if I want to capture the uncertainty around P1, I can use a beta distribution, which has alpha and beta, two parameters. I can set alpha, I forgot. So alpha is M, beta is N minus M. So it's very straightforward, okay? So we have this binomial distribution with some probability death, with some probability survive. I have the data, I follow 10 patients or N patients, M of them are now dead, okay? M divided by N is a point estimate for the probability of death, right? Of course, if I have more patients, I'm more certain about P, or the point estimate of P. Now, this is the distribution, the beta alpha M and beta N minus M to capture the uncertainty around PS. Now, in this case, this is what we have for the transition probabilities. Imagine that I have run this experiment. I had a number of patients, and for example, M1, M2, M3 ended up in this category or in this state. Now, an estimate for P1, of course, is M1 over N, and estimate for P2 is M2 divided by N, and estimate for P3 is M3. Is that right? So this is what we did. So if we look back at the way that we calculated the probabilities, we divided this number by the total. We divide this number by the total. All right? That's what we did. Those are estimates. Now, I want to incorporate my confidence about these estimates. The way to do it is to assume that these estimates follow a Dirichlet distribution. Now, this is the last step of the lab. We want to be able to sample from this distribution. Let's see if I have anything here. All right. So it involves two steps. So if you go back on the transition matrices, so what we have, the first matrix is the data that we got from the UK, right? Now, if we want to generate Dirichlet samples for the probability transition, first we need to generate some samples from a gamma distribution. So gamma inverse, we pass a random number between 0 and 1. Alpha is the number of counts for the first category, and we can set beta to 1 or any other number. Okay, let's go with 1. Now let's copy this formula down. So for this case that we get no, not a number, replace them with 0. Now we calculate the sum of these samples. What happened? Okay. All right, so let's review it again. So first we generate samples from a gamma distribution. that the alpha parameter is set to the counts that we have here. The beta parameter is 1. You can choose any other number. One is fine, or any other number. It doesn't matter. So that's how we generate the samples. Again, hit F9 or refresh. You see that every time we get a different realization. And we calculate the sum of these numbers, right? And finally, in the second table, we want to generate the samples from Dirichlet distribution, which is equal to the gamma sample divided by the total. So let's also lock the H. Now let's make sure that these sums are 0. Okay, all right. So it has 2 steps. The first step is to generate realization from a gamma distribution. The second step is to divide these realizations by the sum of these random numbers. Right? So this divided by this gets us this. The second probability okay? So this is how we generate random numbers from a Dirichlet distribution. So if you look at these numbers that I'm generating, they are very close to what we used before, but there is a variation. And also the sum is always 1, which is exactly what we want. The sum of probabilities should be always 1. Okay? And this is what now I'm using in the model. So if you remember from before, this is what we had, but now I've changed it so that when the parameter uncertainty is on, I read these samples. When it is off, I just divide the counts by the total. Same way that we did before. Okay? I'm sure you're happy that this is the last lecture. All right. Okay, so now, is there any question on this part? For those who are actually doing it? All right. So now let's go back to the parameters. Let's run the model once, assuming that the parameter uncertainty is off. So I want to get 250. Where is that? All right. All right. So you can, just to remember this behavior, we can going to just save these so that, so this is what we had before. Okay. Let's also have a look at some of these estimates. For example, discounted life years for this option is 6.5, combination of 12, and also pay attention to the confidence interval. Now, when I turn the parameter uncertainty back on, let's simulate. Oh, it didn't change as much. Anyway, so this is how it works. So sometimes you see, yeah, like this is what we had before. So here you see that there are more uncertainty and more variation, and also you see some major changes in our estimate for incremental cost and things. Yeah. Yes.
How big a change would it need to be for you to report it as significant? Theoretically, if it's just a small change, do you even note it?
After turning on the,
Yeah.
so until you do, if you don't do it, you don't realize if there's a significant change or not. But, you can change, you can compare, like you can run it once with the average estimates, read the confidence intervals and run it again, see if there's a significant change in the confidence. Yeah. But that's, to be safe, you need to incorporate the parameter uncertainty there. Yes.
So, how is this different than like you're turning on the parameter uncertainty for all of the variables at once?
Yes.
Versus like assessing the sensitivity of like one input that you have at a time and seeing like how much that is that.
So we are not only turning everything on, but also the samples are coming from distributions that are valid, that are reasonable.
Okay.
You know what I'm saying? So if you if you do one-way sensitivity analysis, you are essentially giving the same weight. So if this is your mean, if you put it on the upper bound, lower bound, you are giving everything the same weight. But what we are doing here is that if you have more data, this is what you should see. If you have less data, this is the sample you should see.
You have more certainty about what
you have more certainty about where you are.
Okay.
That's what I'm saying. But I'm sorry, continue.
Just like if you had one input which you were like not sure about at all.
If you have one input.
And you wanted to see like how much it impacted your cost at the end.
Yes. So if for the input parameters that are not informed by data, such as the discount rate, you can do one-way sensitivity analysis. But if they are informed by data, then this is what essentially you need to do. So we have some time we can discuss. We can spend more time on the input uncertainty, or if you have questions about the final project or previous labs, we can use the time for those.
So for when you do the uncertainty analysis, do you want to increase the number of replications just to make sure you're
Essentially, you should do that. Yeah. Again, you should increase it because now you're introducing more uncertainty. So you are enlarging the upper bound, so you need to increase it. Yeah. Yes.
So for this, would you just say, so you could compare the graphs and say that just, it's less spread out with the new version, but then would you just list like, this is how the discount likelihood change, this kind of cost?
Yeah, the main idea is not just to show that they are more spread out, the main idea is this estimate. So in order to get unbiased estimate, we need to do this. And you can see, of course, models may have different behavior, but you see that these are changes after you incorporate the input uncertainty. You can report that, before that, many people don't even report what was before uncertainty because something is okay. Yes. Sure. Yeah. But maybe before you come, is there any general questions about the presentation? Is it on the next week? Yes.
How do you adjust parameters according to age?
Oh, in
age adjustment.
Mortality rate.
Oh. So.
I know if we have like only 3 age ranges, we can do like 3 separate matrices.
Yeah, I think that's the. Yeah, that's if you want to use spreadsheet, okay, the easiest way is to break them down into maybe 3 or 4 subgroups and have 3 or 4 matrices, okay? Uh, the correct way, of course, is to assume that the mortality continuously increases, and for each age, you need to retrieve the probabilities that are correct for that rate. But then that makes it too slow, so you can't run it, essentially. So I think that that's okay if you want to say, okay, this is the matrix for age group X to Y, and then Y to Z separate, and then that's fine. Do you have any question about the presentation day? All right, so you all have 10 minutes. Make sure to, finish on time.
Do you get signal?
I try, yes. Okay. All right, so I see you next week. But I'm going to be around if you have questions.
We have
All right. Do you want to come first?
Sure, I think mine's a little bit easier, and if the question's not right, then I might join the group. So I'm working on one that's doing like steroids and septic shock, and it's basically comparing both 28 days and 1 year later. Is it okay if it's binary, like just alive or dead? Because they don't have the full data. It's the study is like if you give the steroid to people in 3 different groups, either responders, non-responders, or all patients. What's basically does their mortality risk go up or down?
Okay.
And so is it? I mean, so I was doing it and I was like, basically the 2 states are you're either alive or you're dead.
Yes.
Is that okay?
Yeah, I think so. Unless there is some, in between states that they linger before they dead.
But there's not information on that, and that's why I.
Okay, so this paper, is it a modeling paper or just a clinical paper?
This what? Sorry.
Is it a clinical paper? Did they develop a model or?
It's not like I don't think they developed a model. I think they basically were like, this is what it has, and then they compared the two to see how it was.
Yeah,
is that okay?
Yeah.
But then I would be doing it for 3 different groups of people at 2 different times.
Yes.
And then, so how do I incorporate uncertainty stuff? Would I incorporate that into because there's nothing about cost or utility in this. It's
but can you find it from somewhere else? Because like utility, death has 0, alive is 1.
Right.
So maybe you can see
I just feel like since it's so binary, it might not be relevant.
But it depends on the question. What is the question you want to answer? Is it, the idea is to generate evidence for making decisions.
Okay.
It is not that you just want to compare 2 things. It's just which one is better. If you want to.
Or it's like, should you implement it or not? So
Exactly.
if I maybe find some cost information of like the cost to administer the drug, but then I don't know how long. I think most of the treatment is 7 days. So I could do that maybe.
Yeah, and if you just Google, I'm sure something comes up, or make some assumptions. So you know what I'm saying? Like there should be a question.
Right. So the problem is though that like they can die before the 28-day time period, and I don't have the information of like when they die.
Make assumptions.
Okay. So can I assume that like if they made it 28 days, then they received the full? If they did not make it 28 days, they did not receive the 7-day treatment.
5-year survival, 50%, 80%.
I don't know. I think I need to read the. I need to know or the paper or the. Okay, yeah, maybe do that.
My other option was to try and replicate this, which was doing a Markov model for the natural history of antidepressant agents. And so it's saying if you had something that were to improve mortality, how effective would it be? And so they have, it's basically going through this.
That might be more straightforward, and it's up to you. But you can talk.
My other option is to join their group if their project changed.
I mean, it's up to them.
We love her.
But do you know what their project is about?
Yeah, they're doing like the probabilities of flu transmission and the reading group, right?
Yeah, but they are developing a discrete
Theirs is more
events.
difficult than mine, I think.
I think so, yeah.
You guys are doing my group instead.
So we've already committed to the second one.
Yeah.
Alright, I should do it. So which is your question more difficult or their question?
A short question.
Short
Go
question?
ahead.
Simple question about shortcut. How did you copy the formula instead of the format?
Oh, it's a. So I don't know in Mac, but you can if you control copy, then if you go somewhere else, right click, then it gives you this paste special.
I read that what it did in process. Use the keyboard.
Oh, the keyboard? Oh, no, the format I didn't. No, the format.
Our question is about the project. This is the binary that we got, but do you think the place can be strange because there are a lot of dots?
Yeah, that means.
Cluster here. So one could be the reason.
So we're only
Incremental. Maybe they are dying too soon, or maybe it might be correct. It might be correct. So you should.
Because we're simulating a cohort and it's 65.
Yeah, I think if you generate these figures, you can see what's happening. Either this, I mean, this is usually good. This is always good to generate. And what is it that you are modeling? The stroke. So I think time to a stroke or number of a stroke also good, gives you some idea. But this is the first thing comes in mind is that these are patients who die soon or they die early because of a stroke or something else.
So maybe the best way dominate the results.
Exactly, yeah. And if you also show show the frontier, that also makes it more clear.
There's a frontier.
So you can, if you shift
on the secondary.
And what if like our results are not stable because we're doing like 5,000 replications now and it's still not stable?
So for each time, those means have different ranks.
So
I know that's a problem because some of the outcomes have very small probability with a high cost or high mortality.
so then, if are they significantly changing? Are they like the change is significant?
I think like they change the direction.
So then there must be something wrong. Yes. Do you have the same problem with you when you run the in-class lab? So when you run
the in-class lab is fine, but the homework is not. So like the homework is not stable.
Okay, do you want to send me your files? I can look. There must be a guide or something.
Okay.
Yeah. Either a project or the homework.
Okay, sure.
Homework might be better because I know about it. Yeah. Homework is better so that I can see if there's a bug.
Alright, thank you very much.
Alright. So did you decide to join there?
So we mapped it out this morning. And we figured out all of the parameters and everything that we're working with.
Okay.
Now, we're wondering, so basically, we looked at the Connecticut flu data from last year at like the peak of the season to see what percentage of patients arriving at outpatient clinics had flu-like symptoms, and we're using that.
Okay.
But now we don't know where in this beautiful code to put to generate a random number to create the status of the patient.
So
And
the
then-
status of the patient, you can add it on the patient.
On the patient. Okay.
Yeah, like ID status, similar to status.
So would we do like private
Yeah.
patients, flu arrival, flu status? As because it's gonna be
So-
random. So
so-
do we go back to
well,
this random?
No, so the type, go back to it. So it depends on how you want to do it. If it is a binary,
Yes.
you can just go with the Boolean. So it is
Okay.
B or, so that is true or false.
Yes.
Okay.
And then you
But
do
So this is the placeholder. So this is a variable to keep this. Now,
Our biggest concern is trying to figure out what the mortality
it is like, it works similar to ID. So when you have an ID, you need to assign it. It is like the patient knows their ID. This is what the patient, so there is a significant similarity between what you are doing here and the real world. Okay? So this is more similar. So in real world, the patient gives no ID. So this is essentially the brain of the patient. I keep the ID. I know what time I arrive. And now I know my status.
okay.
But
then you
remember,
can go down there and say
okay, so when you create the patient, you need to give them ID. So you pass the ID, and that's how the patient knows the ID. So you assign the ID that is being passed
Yeah.
to the memory of the patient.
Okay.
That's what it is. So now, what we can change here is that also pass the status, the fluid status.
So by val this way.
Yeah.
By val
Mhm.
patient arrival flu status.
Yes. As Boolean, exactly. So
As
it is-
Boolean.
Yeah.
Okay.
So now you read this and update the memory of the patient, which is set the patient arrival status equal to what you are passing.
Okay.
All right. So if
Okay.
you do that, now you know. Now the patient knows their fluid status, but you
we
don't.
don't.
But you don't.
Yeah.
So that's what you do here. That's what you need to define a public property.
So how do you know if it's only 5% of the patients? So like it's
Yeah. So now you can do this. If you
and then it would be
it should return this value. The patient arrival value. That's what you return. Essentially, you want to make this private variable public to others.
Okay.
then how do you assign true or false?
So we will do it now.
I like to jump ahead.
So this
Yeah,
is.
I like to think ahead, whereas like what is this? Whereas like we haven't done it yet. This is why I'm not good at coding.
It's good. It takes a while, but then everything becomes clear.
Okay.
End property.
I don't think you saw that.
Okay.
I'm like, what about this?
All right, now you want to assign their status. Okay.
Yeah.
So what we're doing, we're assuming that at the time that you create them, you assign their status. So you can go back to the brain. Here is the urgent care.
Okay.
When are we creating a patient? When they arrive.
Yeah.
Right? So go to this initial. This is
Create a new patient.
yeah. So anytime you create a new patient, I think this is one. We also create a new patient. No, I think this is the only place we create a new patient. Now, so here we are passing their ID. Now we also need to pass their status, their fluid status. Okay? So similar to what we did in Excel.
Yeah.
You can define a variable, call it. Maybe I can do it. So let's define theme status. Okay, as Boolean. Right.
Yeah.
Now
And we
let's
call that other one.
let's draw a random number if the R&D is less than maybe 20%, you said?
0.05.
0.05. 56?
Yeah.
Right. So
Should there be another 0?
It's
No,
not.
okay.
If the random number is less than that, change the status flu, which is true. So that's what you assume. I mean, it's better to use a better name. So it's a flu status. Yeah.
Yeah, we are.
So then,
Yes, we are.
flu status. Okay. Otherwise, make it false. Okay.
Is our big question I'm failing to understand the temporality, right?
That makes sense.
If you're in
Okay.
state
Yeah, and then
0
here,
times 0,
which argument are we using? Is it the last argument?
this is saying
I think it was the last one.
Yeah.
So now pass this.
that is
Right?
You
So this
Okay.
is so every time you create a patient, change random number. If it's less than this, this is similar to Excel. Similar to what we have been doing. So then that's flu says true. Pass it here. Now you have a patient. You assign them an ID and their flu status.
Yeah.
So then
Okay.
all of these
So
are
this
1
can
year.
go
So we can do the same thing with the
for the healthcare worker
Yeah.
for
vaccine status.
That's the
And I think if you have access to a Windows machine, that makes your life much easier.
Yeah, Windows.
Yeah.
Okay.
If you can remotely connect to a PC.
Okay. I can rent a laptop for the weekend.
combine that 2 times a third.
In terms of then checking the status, that's not an event. So,
Checking the status.
So in the waiting room, if the patient with the flu shows up and we're checking the status.
So you can assume this that every time. So where is the here on the waiting?
Yeah.
Where is the waiting? So this is where we are adding the patient.
Yeah.
So you are passing the patient. So here, if you want to know their status, you can just use this patient dot the status of the name. So if you use it on PC, it gives you all the so it is much easier to do.
Okay.
So then you can check the process. And now, I think independent of the status, when a patient joins, you need to scan the room, see how many patients you have. So essentially, you need to write a for loop, go through all the patients in the queue, in the waiting room, count the number of patients who have flu. When you divide it by the number of patients, that gives you the probability that you contact with someone with influenza. So you add the patient to your queue, then go over the queue. You know how to do it? We have a for loop, and then you define a variable to represent the object.
Okay.
So for loop, I mean, you have it. We have a lot of these examples.
Yeah.
You can find one of them.
Okay.
Count the number who are infected. You know the total number in the queue. It is just the collection dot count. The name of the patient can give you that. So and then you have this transmission parameter, which is whatever you call it, alpha, whatever. So that parameter times the probability or the prevalence of infection, that gives you the rate of the transmission.
So the probability you come in contact times probability.
On the Excel, we'll want the transmission parameter on the Excel then, right?
You want to report it or what?
We found that it's between 30 and 50% if you are in contact with someone with the flu, you have a 40% chance to live.
So can you do the if contact, like, so if with the probabilities, then like assign another random number if it's in that number.
Is your question quick or?
You know, then the contact of it. So it's like multiple ifs.
Yeah, but I think that's what the for loop is too.
Do you
Because
want
you count
to
it first, and then like with all this information, then count it.
So the amount of people with flu divided by.
Yeah, because it's not just like
I spent a little bit of time with them.
Okay,
so
that's
someone
fine.
can share.
So, because it's not just the remember that 4 million sent us, it's like the.
Yeah, that's what I was trying to figure. So
So this is the probability that you. So the counting, the for loop part is counting how many people you have flu status, divide, and then you divide it by the people who are in flu. That's your probability coming in contact with someone.
that's the prevalence of the flu in that room at that moment.
Oh.
Yeah.
So I'm just wondering if that 40% goes on that front perimeter page or not.
Well, then how does that go? That's not taking into account the number of patients. He wants us to mimic this more scientifically. So this is to add a new patient to the room, check status of the patient, right? What was this for?
But there's no diff.
This was
There is that, but it's just binary. You don't know if they died because of this or not, it's just whether they died.
flu status, to bring the flu status to it, right?
Right.
Can you? There's a
Basically, you have like a slightly
death
it should be times.
Yeah.
And this
But we don't have that in our
is
data, so we were gonna look into the
this.
literature and then try to come
Yep.
up with that.
So then it's not binary anymore because when you're here, there's a chance that you go.
Because it's about.
Wait, should that not be flu status?
Either death
It is.
or
I'm just shortening it so I remember it.
Yeah, also because we have another check that's gonna be 3 options, we need to figure out what that
Patient
is.
model where patient comes in and it stays,
Yeah,
and it
that's
moves,
good.
and it stays, and it moves, and it works with the
Yeah,
system.
I'm not gonna like
Is it more of a
Yeah,
modifier?
Yeah, if you have 3 options, what is that? Integer?
Okay.
Because
1 year.
you have death.
Right.
Integer was the, no, it was double, the one that was able to.
Count.
Why is that a different name than this
Death
one
or
in
post
here? So I don't think we need this one.
procedure.
Yeah, no, that
So
was.
I think you should think about it more. When you have an additional state, essentially, which is death.
Why
You
is
have
it
absorbing the state, but it's in a state.
Okay.
So I think this is a good idea.
Okay.
Yeah, anybody.
We have created a new patient. Why isn't this the same? Very.
I think it should have been. Shouldn't it?
So when we
Because he was like, because he typed in flu arrival status or whatever, and he said that because it's Boolean is true or not. So if you do flu status true, then you know that they have
That
a
should be
flu.
our patient or
If you are using that,
And at this point.
Yay, I'm contributing! I'm not even officially in your group yet.
alright.
Please join.
So if the rates, then
So then-
convert the
Right.
rate into the
At this point, we can do the healthcare worker status the same way.
So we're gonna have to do that at
It will be
different
the remaining
time too, right?
Okay, got it.
It should be before the patient.
But would you assume also that the healthcare worker,
Right.
oh, well, they're not coming in with like the contacts, they might get this.
But they could have the
So,
vaccine.
Yeah, we're
It could be
doing this,
vaccinated.
yeah, the initial check is for the vaccine. We are then assuming that they come to work.
I wonder if we could do that and
Yeah.
create.
Yeah, we're
But if they
assuming.
have the vaccine, which they are required to have, then they shouldn't have the flu, right?
So, well, there's a percentage of
Reasonable.
it's lower.
It's lower.
Which is why.
Yeah, but you're still pretty safe.
So we wanna model the.
It's like
just
55%
general-
effective.
So it would be like percentage that they come in contact with that person.
Okay.
So it's like probably they
It's
come
a
in contact with that
science
person.
It seems low that like
No.
if you have a 90%
So what happens?
three-year mortality.
So,
Because you
what's the
basically
next,
play.
so when we're
You're playing the
checking for
mortality game with an
the
8%
flu
chance of
status
death about 10 times.
in the room, we were gonna do flu,
That's
no
what happens
flu, or
over a 3-year
exposed,
period.
meaning that they were
So if you
exposed.
play it 10 times.
Because when
But
they
they're
move
not-
in, cause then they won't pass it in the
90%
health
Yeah.
check. So we wanted 3, what, if it's
It's
not
not
blue, is
blue.
it double?
Right? Does that make sense?
So you want to do 3 Because when there is, so what's the difference?
So when they,
Exposed don't transmit?
yeah,
transmit.
so when they first come in, either you have the flu or not, and then you're sitting in the waiting room, there's a chance you get the flu, so if you didn't have the flu coming in, and then you did get it when you were in the waiting room, you'll then be exposed.
But you're not.
But then
What
you
are the odds
won't
that
keep,
you,
yeah, you won't keep
that this
spreading
takes you down to 10% chance?
because it was like 2 days until you're actually gonna get the flu.
Yeah. Yeah. If you, I mean, you can do it. It's not that difficult. It's just.
That's your average 5%.
Should we do a separate, like a separate status, or just do?
I would think the best way is similar to what we have here. The exam room options. This is enough. So define something similar to this. And the good thing about coding is that you can copy and paste whatever you like. So use it. So if you go to patient instead of you can define it maybe on top. It doesn't matter where you define it, but Command Z.
Are you trying to?
Yeah, copy that formula. Copy that
from exam room.
Yeah. Oh, it's command. All right. Now just change it to.
And we can do 3 there.
Yes, you can do the 0 is maybe susceptible, exposed, infectious. But now the
I'm just replacing the way the G6 was before.
So now you're left with
All right.
a
Okay, now the only thing that you need to implement is that similar to. Do you see we have this exponential thing? We need to implement something similar to this that so that we can generate random numbers from, because now you have 3 outcomes. Remember this is
No, he's saying why does that
CDF?
Yeah.
Relapse in cancer when you die, it means you shift
Let's see.
cancer. How does it happen?
Then you have to pass arrays and stuff. Maybe don't do it.
Why are you using
unless you want to, I mean, you can do it and then finish it, and then if you have time, I can.
Okay.
Because then you have to work with arrays, which I don't know if you want to spend time at now. Maybe.
Yeah, this is already over my head,
Yeah,
so I'm okay.
Yeah, so just assume that there are 2. There are either susceptible or infectious.
Okay.
That's what I'm asking.
Okay.
It may not be the.
Is that one of our assumptions that like?
No.
Or do this. Assume that they don't.
Abby wants to make cancer a death.
Oh, okay.
We have really good luck picking problems. I'm sorry.
Yeah, we have 100-day all-cause.
No, assume that I mean, you can make it easier that they don't transmit while they're waiting, but they can transmit to the doctor. Oh, but then
The doctor has a vaccine.
But they can transmit to the room, so maybe they can make the no, huh? Maybe not.
Could we do just the flu status of people who arrived with no flu?
Yeah.
And then we can make them exposed or not exposed, and then that would be Boolean? Because the people with flu are going to stay with flu.
So then we're just not, do we count them?
Because we're only really interested in the people who come in with no flu who all of a sudden get flu, right?
I think I'm gonna stick with the markup.
It's officially scared.
It's just
So,
too complicated.
this might lead into a really good question. Completion of the project.
Upon presentation.
We're gonna bust our butts. We will.
No, that's the thing. No, again, there's always plan B.